In this video we will use Fermat's principle to work out the distance to the apparent horizon. So we have spherical Earth, height h above the surface of the Earth with radius r. We have the apparent horizon, which is determined by the fact that this light ray is emerging tangential to the Earth's surface. Let's call it angle theta. Now geometrically, we have this right angle triangle, so theta geometric, we call this thing theta geometric, and that is determined by the fact that since that's radius r, we get r plus h cos theta geometric is equal to r. So theta geometric is 1 over 1 plus h over r inverse cos, and therefore the distance to the geometric horizon is r theta geometric, that's that distance there, is theta inverse cos of 1 over 1 plus h over r. Right, that's what we get if we did not have refraction in the atmosphere. To deal with refraction, we're going to use Fermat's principle. So that says the integral dt is, the variation of that is 0 between the two endpoints. That determines the curve. So we're going to have a refractive index n, which depends only on the radial distance. So this becomes delta integral. Well, the velocity of light is c over n, and that's equal to ds by dt, where s is arc length. This is n over c ds, which is 0. Let n naught be n of r. This is the refractive index at the surface. So I can divide this by n naught and I can multiply by c. Now ds squared is dr squared plus r squared d theta squared, which is r squared plus dr by d theta all squared. So it's d theta all squared. And therefore that's delta the integral of n over n naught root r squared plus r prime squared d theta between theta equals 0 and theta equals, let's just call it theta for this apparent horizon. Now let us rescale things. So let's write r as capital R times rho. So that's delta the integral of n over n naught root 1 plus, so rho squared plus rho prime squared d theta. Let f be n over n naught root rho squared plus rho prime squared. And n here is a function of rho. You'll notice this has no dependence on theta, so we know that rho primed df by d rho primed f minus that is a constant. So that's n over n naught into f, which is root rho squared plus rho prime squared, minus rho prime times the derivative of that term, equals a constant. And then over common order is a rho squared. And the constant is given by the fact that at the point of the parent horizon you have rho of r equal to 1 and rho prime of r equal to 0. Actually, really, that should be theta at that particular point. So putting that in here and using that n equals n naught at that point gives 1 there. So n over n all squared rho to the 4 is rho squared plus rho prime squared, which implies that rho prime squared is n over n naught squared rho squared minus 1 times rho squared, and therefore integral d theta is minus the integral d rho over rho root n over n naught squared rho squared minus 1. And this is from naught up to theta, and this is from 1 plus h over r to 1. And we need the minus sign in because that's greater than 0, and we have to take a square root here. And this thing is then greater than 0. So that's correct. That's the integral 1 to 1 plus h over r. d rho over rho n over n naught squared rho squared minus 1 square root. In the case that n is n naught as a constant, then this is just an inverse sec integral. Well, let's write rho is 1 over sigma. So this is the integral 1 to 1 over 1 plus h over r d sigma over root n over n naught squared minus sigma squared. And let's just make sure we've got the sign right. So that should have been plus and minus. Now let's suppose that n is, or n over n naught, is equal to 1 minus alpha sigma minus 1 plus higher order terms, which we're going to neglect. So we need to do an integral. Okay. We'll end up with the integral of root minus a sigma squared plus 2b a sigma plus c to compute. And that's equal to integral d sigma over minus a sigma minus b squared plus c minus b squared plus square root. There's an a in there as well. ab squared sigma over root 1 plus a over c plus ab squared sigma minus b squared. There. Let's multiply by root a and divide by root a. So that's 1 over root a. And this is just the inverse cosh minus sine of a over c plus ab squared square root times sigma minus b plus a constant. We were looking at n over n naught is 1 minus alpha, sigma minus 1. So n over n naught squared minus sigma squared is equal to minus 1 minus alpha squared sigma squared. You get cross term here. That'll give me a minus 2, actually let's make them to a plus 2 alpha 1 minus alpha sigma plus the constant term is 1 minus alpha squared. So therefore a is 1 minus alpha squared. B is alpha over 1 plus alpha, and C is 1 minus alpha squared. So C plus AB squared, 1 minus alpha squared, plus, no, sorry, 1 brackets that way around, plus A 1 minus alpha squared times alpha squared over 1 plus alpha all squared. And that's equal to 1 minus alpha into 1 plus alpha, 1 minus alpha, plus 1 plus alpha, alpha squared over 1 plus alpha all squared. So that's 1 minus alpha over 1 plus alpha into 1 minus alpha squared plus alpha squared is 1 minus alpha over 1 plus alpha. So the integral 1 to 1 plus h over r minus sine d sigma over root n over n naught squared minus sigma squared is equal to plus 1 over root 1 minus alpha squared cos it's minus 1. Okay, a over c plus ab squared is 1 minus alpha squared over 1 minus alpha 1 plus alpha, and that's just 1 plus alpha all squared. So you get 1 plus alpha into sigma minus b, I want to change that. So that's equal to top sine 1 over root 1 minus alpha squared inverse cos 1 plus alpha over 1 plus h over r minus alpha. The lower limit will give me one plus alpha times 1 over 1 plus alpha inverse cos of 1 is 0. So that's what I get for the location of the apparent horizon. So the distance to the apparent horizon is just r theta, is r over root 1 minus alpha squared inverse cos 1 plus alpha over 1 plus h over alpha minus alpha. Let's look at the special case when alpha equals 0, so this is the case when the refractive index is constant, so this should give me the geometric horizon. So we get R inverse cos of 1 over 1 plus h over r, which is indeed the geometric horizon. So that's a consistency relation. So let's have a look at the ratio of d over dg, geometric, for general alpha. That's going to be 1 over root 1 minus alpha squared inverse cos of 1 plus alpha over 1 plus h over r minus alpha divided by the inverse cos of 1 over 1 plus h over r. Let's call this quantity k. Now we need to evaluate the inverse causes. This thing could be very close to 1, and so is this one for h a lot smaller than the radius of the Earth. H is no more than about 2% of the radius of the Earth, so this is an excellent approximation. We have cos of lambda is 1 minus a half lambda squared plus higher order terms. So from here you have, as an approximation, that lambda is the square root of 2 into 1 minus cos lambda. Like that. In other words, inverse cos of capital X is root 2 into 1 minus x. Approximately. There's no approximate sign there. So k is 1 over root 1 minus alpha squared, so approximate. We get root 2 into 1 minus 1 plus alpha over 1 plus h over r, say 1/2, divided by root 2 into 1 minus 1 over 1 plus h over r. It's 1/2. Those cancel. Well, 1 minus 1 plus alpha over 1 plus h over r plus alpha is 1 plus alpha into 1 minus 1 over 1 plus h over r. So that thing is the square root of 1 plus alpha over root 1 minus alpha squared is 1 over root 1 minus alpha. So this is the ratio between the apparent horizon and the geometric horizon. Okay, well, let's put some numbers in. We know that the ratio of refractive indices is 1 plus alpha sigma minus 1. That's how we define alpha. So in other words, alpha is equal to 1 over n naught dn by d sigma at sigma equals 1, which is minus 1 over n naught dn by d rho at rho equals 1, which is minus 1 over n naught dn by dr times capital R at r equals r. Well, now we can look these things up. N naught, we're going to take that to be approximately 1.00029. This is for typical atmospheric conditions. We have the dn by dr at the surface of the Earth. We're going to take that to be minus 3.9 times 10 to the minus 8 per metre. And we're going to take the radius of the Earth to be 6.371 times 10 to the 6 meters. This gives me a value of alpha of 0.248 and therefore a value of k of 1.153. We can compare this to 7 over 6, which is 1.166. So k is approximately 7 over 6, which shows that the apparent horizon under typical atmospheric conditions is further away than the geometric horizon by a factor of roughly 7 over 6.